So, hmm, works without the what? Well, okay, it works. It just depends on what program you're trying to run. So, uh, probably, but we can look at that later. Rippy, let's test yours. Come on, let's go. Come on. All right. So, all right. Rippy, let's see. Get out. I need to get the EEPROM out. Yeah, I'll let you do it because that way, if you screw it up, then it's your fault. You can come around so that you can. Shane, are you on Twitch or did he send a message? Uh, well, I've got a paper clip right here. Yeah, but it's just. He means for the.
Okay. Oh.
Is it open or?
No, this came out. I don't know where it is. That probably went into this one. I'm gonna guess. I think. Oh crap. Do you have the? We'll figure out where that one went. These ones like to slip out a lot.
Yeah.
I have no idea why.
Well, okay.
Yeah, I have no idea why that one likes to slip out so much, but that's just the case.
Well, you're gonna have to figure out which line that was because it's not gonna work if.
It's gone.
Yeah.
The yellow, for some reason, of all the ones, like to slip out the most. I really hope that didn't just pop out. And before I actually just messed it up.
All right. Well, while you're doing that, let me get my barrel plug so we can power it. Do you have the barrel plug power on that, or were you using Arduino power?
I mean, I don't think the barrel plug's plugged in.
Okay, well, that's okay. I'll just use mine if I can find it.
Which one did the EEPROM connect into? I know that's for one of the logic things. Yeah, I'm pretty sure it's this one.
Well, we'll find out. Okay, and then go get your barrel plug connector because.
Alright. That came out, but I'm pretty sure it wasn't for an
Okay, go get your or the barrel plug so that I can power it. Okay, there's two things that I wanted to mention. One was that I'm an idiot, and you remember the business with the dots last time and the assembler complaining about them? Well, it's actually because we have to give a command line flag to tell it to expect the dots before directives, and I forgot about that, so.
Okay. So I have no idea if this is working, but
Well, the screen's not, so.
Well, let's definitely connect to the power.
Yeah. All right. Oh, well, there's no ROM in it because I haven't programmed the ROM yet. Well, not to turn on, but it should. I don't know. Okay, so.
I mean, that's something that might be weird. I didn't know exactly what pin I was supposed to have, but I'm pretty sure that's right.
All right, so two things. One, let's program this again. So it's mini pro. Then it's what is the command for? I need to write this down. Yeah, just leave it here. And okay, so let me go to his playlist for all of these because I need to write down the. All right, so I need to get to the programming part. Because I forget the command. All right, here it is. Okay. All right, so we need to do mini pro dash P AT28 C256 W A dot out, which was our hello world, and dash P, not dash O. Okay, so I've got the EEPROM written to Rippies, and now we'll test it if I can get it in. Did you have to wire it up this way?
I mean, oh, yeah, I mean, it's a rat's nest, but it doesn't have to be that much. Oh, it's a rat's nest. You can still get hardship though. See? Yeah. We just rat nest it around it. Yeah. Not over it. Oh no, did it get bent?
Yeah, and it's going to break at some point, so.
Well, that's less than optimal.
Yeah, well, I ordered some.
So make sure it's, yeah, okay, it's facing that way. Okay, I got you.
Okay, got it?
I think so. I mean, when this whole thing popped up, I'm pretty sure it's still working just fine.
Well, the screen's not, but.
I have no idea. I don't know why this isn't working. Unless this is the only thing I might be worried about, but like this is connected to power.
I don't know.
I mean, like, I'm pretty sure that, I mean, the screen was the easiest thing to do there.
Yeah, well, we'll figure it out. Okay. So, pain. Okay. So yeah, so I want to talk about a couple of things then today. Um, and the first was the manual for VASM. Okay, so I was an idiot and I forgot about um, there's a flag, command line flag that we need to use when we use the VASM old style. If we add .dir, then all of the directives require a dot at the beginning of them. So that's the way that Ben wrote his code, and I just forgot about that. So if we go back to our sample program here, this is basically the thing that should print hello world to the screen. And so we'll know that things are working if it in fact prints hello world to the screen. Then the directives, and I removed these last time, I'm going to put them back in. Um, Why is that all green? It's weird. Uh, no, I think it's just the syntax highlighter that I used. There we go. That one's better. Okay, so I just put the dots back in on the directives, and that way we can still do it. So when you compile or assemble the code, then we'll have to do it with. Let me blow this up so that it's more readable. Um, so it's VASM old style, and then we need to do dash dot dir, and it's uh, hello world. Oh, and then dash fbin. Okay, hello world.fbin, or sorry, that's the command, right? And so the two options here, fbin is so that it outputs a binary file that's appropriate for programming to the EEPROM, and then the dot dir is so that it expects a dot in front of the directives like the Word and ASCII and things like that that we're used to because uh, when we did this in ARM assembly, we put dots in front of a lot of the directives. Okay, so that at least keeps it somewhat consistent. Okay, and then it just went to a.out. That's the default here. Um, and if we double check, then of course a.out is in fact 32.768. And for the EEPROM, it has to be precisely 32.768 because that's the amount of data on or space on the EEPROM chip. Okay, so make sure that it is that. Okay, so I want to go back to the code for a little bit. This was the worst way possible to do Hello World, but essentially what it's doing is there's a little bit of beginning stuff to turn on the screen and get everything initialized. Okay, and then the rest of it is basically just load the ASCII value for H into the accumulator and store it to port B, okay, and then do some other stuff. So this would, basically tells the screen, hey, the data I want you to display is this binary thing, and then I'm going to send a command to the screen, um, and so that it will actually display and so on. Okay, and so there's one of these basically for every character, which is of course the most inefficient possible way to do this, but it works. And then it's going to go into an endless loop where it just sits there in this endless loop until you power the thing back off or hit the reset button. Okay, and then the last thing I wanted to talk or make sure we're clear on was the reset vectors and the non-maskable interrupt vector and the interrupt vector locations, right, are all at the back of the EEPROM, and so these have to be there. Right now, we only have the reset one in, which is the reset location, of course, is here, and it's going to be at 8,000. Okay, so if you just say dot word reset, right, then it's going to put the address of whatever the reset routine is, and since that's the very beginning of the code, and we designated this to be at org 8,000, that's where it will start. Okay, and it doesn't have to be 8,000 in general, but it does for us because that's the beginning of our EEPROM, right? So we basically are allocating ourselves 8K, or sorry, 32K for the EEPROM. We don't have to start at 8,000. We could start at 9,000 or something a little higher up, but it makes sense to start at the beginning, right? And in terms of like architecture or how the different machines of the era would have used this. it actually was pretty similar. So the Nintendo, um, your program code also would start at 8,000. So you had on the Nintendo, you had 32K available for program, 4K available for characters, and then the rest of the memory space was allocated for the I/O devices like the screen and the audio chips and those sorts of things. And RAM, obviously, you needed some of that. Um, and let's see what else. Oh, and then your character uh, data, right? So your the art basically that would get displayed on the screen. Commodore, kind of the same thing, right? Where was it that programs that were in BASIC went? Where did we put BASIC programs? That's where they had to start, okay? But machine language programs don't have to start there. They can. But often you would start programs at 8,000 hex or C1000 hex. Uh, and you were basically doing so to avoid memory space where the kernel ROM was or other things. And as we discovered in BASIC, right, what you had to be careful with which addresses, uh, like you had to keep track of that, right? If you wanted to put, well, like the program that was print without printing, right? How did we do that? Yeah, you poked data to certain memory addresses, and those memory addresses corresponded to screen memory, and then stuff happened. Okay, so the every time basically you're storing to an address, right? The basic equivalent would be poking. Uh, and anytime you LDA from a memory address, that's the basic equivalent to peeking. Okay, um, so even though the peek and poke seemed a little silly, like the reason I wanted to do a little bit of basic before we got to this is because then you didn't have to learn the actual machine architecture at first. Okay, but eventually, back in the day, right, everybody would hit the wall with basic where it was no longer worth doing things in basic anymore, and you had to make the transition to machine code. Like, put on your big boy pants. It's time for machine code. Okay. Yes. Well, that's a good thing because Java is a hot mess. I hate Java. So, how did that go again? I didn't quite catch that. What did you think? Yeah. So, okay. So anyway, so what I want to start to do is sort of bifurcate our progress slightly. Okay. One is we still, hopefully we'll get some of these dang breadboards to work. It'd be nice if we had at least one of them that worked um, fully. Um, well, we'll test it. Well, I thought I put the correct EEPROM on it. Oh, no, but we fixed that last time, right? I think so. I just removed the dots because I had forgotten about the dot dir, right? So it should be okay. We'll try it. Okay. Um, anyway, the other thing I wanted to do though is for the ones that we think aren't working, right? This is where the Arduino is super handy, right? So that we can see what is it actually doing, what data is on the data bus, the address bus, the read write lines. And if that looks like what it's supposed to, then that tells us, okay, at least the code is working. Maybe the problem is the screen or something else. But if we're not getting the correct instead of instructions, reading from the data bus and stuff, then there's some other problem. Okay. So the Arduino is there to help us. Okay, but like I said, what I want to kind of do for right this instant is to bifurcate our tasks into breadboard on the one hand, and hopefully getting at least Hello World to work. Because once that works, we're in business. Okay, and then the second is, well, we did a bunch of programs in BASIC. Now what? Let's do them all again in assembly or that sort of thing. Okay, so we'll program in assembly, and no. And you know why there won't be a tokenizer? Well, I don't know. Maybe I'll do that just to torture you guys. No. Um, huh? You don't want to graduate? You can still drop it. So, um, I've always been curious what would happen if, like, the entire class dropped? What would, well, maybe not the FBI, but the dean. Yeah. So, okay. Um, anyway, uh, so I'm gonna have you guys do some programs, assembly programs that have nothing to do with the breadboard, uh, at first, okay, and then I want to have you guys write at least one program that will involve the breadboard, okay, but you're going to write the core of it without the breadboard, because so the very last thing, and we'll talk about this, I think maybe Tuesday would probably be the right time to do it, would be interrupts, okay, so um, we have here on the thing 5 buttons, right? Plus the reset button. And the reason that it's 5 buttons is because how many different uh, pins or how many lines do we have coming off of the 65C22? We've got 16 of them, right? The A bus and the B bus. And how many do we need to control the screen? 11. Okay, so it was 8 for data and 3 for control of the screen to send commands to it. Okay, so there's 11, and that leaves us with 5 unused things on the 65C22. And so let's wire up 5 buttons to it. Okay, whatever. We could have done a combination of buttons and lights. Just the way Ben chose to do it is it's 5 buttons. Okay, great. Um, and so the if we think about, okay, what was the first kind of program that we wrote in, well, okay, a little bit after that, an actual program in assembly or basic, right? I had you guys do the Fibonacci's, right? So let's do the Fibonacci's, right? Uh, in assembly, okay? And then what was sort of the other example that we used to write them? Like to start looking at recursion, what did we do? What was our good example? Like in back in CS-241, what was our recursive example that we did in class? What that was what you guys did as an assignment, but what did I do as the demo in class? I did the factorials, right? Okay, because that's also could be defined either iteratively or recursively, right? Makes sense. And so let's do basically the same thing. Okay, there is one minor problem though. What is required to do the factorials? How are they defined? Well, I need some base cases, yeah, that's fine. But what else do I need? I need a multiplication routine. And guess what this processor doesn't have? Doesn't have multiplication. Okay. Well, okay, yeah. So you can do multiplication with repeated addition, or we can just change the program, and instead of doing multiplying everybody, why don't we just add them instead? Okay. Now that's not factorials anymore. Okay. What we would be generating are triangular numbers. Uh, yes. Okay. So Rippy's point here about the shortcut is, so the triangular numbers. What are the triangular numbers? Like, how are they defined? Yeah, if you add the integers from 1 to something, then if you drew dots out on a piece of paper or something, it would look like a triangle, right? And then the sum of those things is, there's a nice formula for it, and that's what Rippy's referring to as the shortcut. Okay. What is the shortcut? So if I want to do 1 plus 2 plus dot 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 plus n, it's that, right? N times n plus 1 over 2. Okay, so that's the shortcut. Let's pretend that we don't know the shortcut. Okay, and I want to add, so we'll define this to be Tn. Okay, and so that would be the iterative way to approach it, is you just add 1 plus 2 plus 3 plus 4 plus until you hit whatever your n is, and you'd have to have some sort of counter to do that. Okay, but then let's see. So that's the iterative way to think of it. What would be the recursive way to think of it? Well, the yeah, this triangular number is n plus the previous triangular number, right? And then what's the base case? What's triangular number one? Just one, right? So then your base case is, well, there we go. Okay. So it's essentially just the same thing as the factorial, but instead of multiplying, we're adding. And the only reason I'm doing that instead of multiplying is because, well, we don't have a hardware multiplier. And so in order to not have to worry about that problem right now, we'll just do addition instead of multiplication. Okay. Right. Okay. So good. All right. So eventually, what I want for the breadboards, okay, is going to involve the program that you guys are going to write, which will be to do the Fibonacci's. Okay. But we've got buttons on this thing, don't we? Yeah. So what about if we had a program where when you hit a button, it increases the number that's on the screen, and that number, say, starts at 1. And when you hit another button, it computes and then displays the Fibonacci number of the thing that you put in, right? So let's say that your screen starts with the number 1 on it. And if you hit the button that you're going to call enter, then what should it output? The first Fibonacci. Okay, so let's say you hit the increase button until you get to, say, 6, and you hit the enter, then it should tell you the 6th Fibonacci number. Okay, all right, so that's kind of where I want that to go. But what is the core of this? There's sort of two things to consider, right? Well, maybe three things. The core of it is actually just computing the Fibonacci's in the first place, right? And that can be done independently from the breadboard. Okay. Then there's the button and that sort of routine, which is, of course, not independent of the breadboard. Okay. And oh, by the way, breadboards kind of suck, don't they? So guess what I found? Not, well, yes, those are called PCBs. Okay. So I'm going to order a couple of them just to see if they work. And then I'm going to make Rippy, who is no longer a free elf, solder all the parts together. Okay, maybe I'll make Evan help you. No.
Dude, the last time I was in charge of a solder, like the third floor of good was almost broken.
Okay, well maybe then.
I mean, I can solder.
No, that's the one problem though with PCBs is that we'll have to solder some stuff. Okay. So anyway, I'm going to order. So there's a dude out there on the internet that has open sourced PCB designs for the Ben Eater 6502 project, which is exactly what we're doing, right? And so I'm going to order a couple of them as a test, and basically what that would replace is the rat's nest of wires, okay, which would be kind of cool. Okay, so so there's that, and then we'll kind of put the breadboards away and get back to doing this on the Commodore Live. And that'll be the point at which you guys will be actually using the actual hardware upstairs and actual floppies, and it's going to be great. Nope. I mean, you can still use the emulators, but it's so much more fun to actually do this on a real computer. Okay. Okay. So, um, so in terms of emulating the code, okay, we can do this. I mean, heck, we could use the Vice emulator, but for simplicity, what I thought we could use instead is um, this thing called Easy6502. So let me, um, blow this up a little bit. Okay, so a guy named Nick programmed um, and wrote this nice page, okay, called Easy6502, okay, and this page has a really nice demo, basically, of where in an emulator he's made a very, very simple computer, okay, that does nothing more, but that has this tiny little screen attached to it, and I forget the dimensions of it. It's not very big, so it's a screen. And how you write to the screen is by putting data in certain memory addresses. That part isn't shocking. And then the end goal of all of this is he makes a, sorry, let me find it. Here we go. So we'll assemble it, we'll run it. I did lose. Right? So he walks through basically programming the snake game, right? On his little screen here. And it's kind of cool, whatever. Okay. But in particular, the system that he's using to do it, okay, without the code here is oops. Let me go back to this version. Okay, um, and so just here's a simple demo program that he's got running. Okay, nothing particularly exciting. Um, and the fact that there's a screen here is not really like we can ignore that part for our purposes. Okay. Um, and go through and basically delete a bunch of this stuff. But in particular, there's two things that this gives us. Okay, the first is the fact that we can single step through the instructions. Okay, and the second is that we can have a monitor. Okay, so for example, if I look in memory here, and let me turn off the debugger so it starts running. So you see how these memory addresses are changing? Right? Uh, I can change this to start at like, let me start at 0, 1, or sorry, at 0, 1, 0, 0, and let me go length FF. Let me come back down to the back of this here. Okay, so you see how this is changing a little bit? What is the first page of memory on this thing? What is it used for? Yeah, it's used for the call stack. Okay. Um, oops. I think I went too far. Yeah. Okay. So here, we basically see, I should have gone one more than FF, which would be 100. Okay, so 256. Right, so we've got our call stack, and in this particular case, this particular program, once it goes into the draw loop, it basically is just looping. Okay, so there's no stack usage because it's not doing any sort of subroutine calls once it gets to that point. Okay, now if I reset it, and let me turn on the debugger. Okay, and now let's look at our call stack. Okay, so what is the stack when we reset the thing? It's all zeros. But if I step, what is it at first? 0206, okay? And the reason for that is because the place it puts stuff in memory to start by default is address 600 hex, okay, whatever. But, okay, so if we step through this, right, what it's doing is we can see what the program counter is, and we can see it drawing stuff. Okay, great. But in particular, we've got our loops here in terms of draw map, gen map, loop, and so on. Okay. The init routine, where is that? Okay, down here. Okay, so it's doing some stuff. And so what it's doing here is drawing the walls, basically. Well, semi-random, right? Okay, so it's got that. Yeah, it is. Okay, so 0602, right, is basically at the start, the very first thing there is a jump to a subroutine, okay? And the how do I know where to come back from when I've done init? Well, it would be 0602 plus 1. Okay. Now, the reason for that is so JSR init, right? How many bytes is it going to take to encode that instruction? How many bytes does it take for the opcode? For the opcode part itself, just 1 byte, always. Okay. Uh, that basically says it's this instruction versus that instruction. Okay. But a JSR is going to need 3 bytes. Okay. And the reason is opcode, jump to a subroutine, and then where are subroutines? They're in memory, right? So what do I have to give the thing? I have to say where in memory to go, and that how many bytes does it take to store a memory address? 2, right? Because it's a 16-bit memory space. Okay, so it'd be 3, right? How do I go back? Okay, so I go back when you hit an RTS. Okay, so JSR is kind of like branching and linking on ARM, and RTS is kind of like the ret on ARM. Right. Okay. So when we in ARM did a subroutine call, meaning we branched and linked, okay, what happened when you hit the BL instruction? Okay, it changed the program counter so that you went to a new place in memory to get more code. Okay, but what did you have to do at the very beginning of the subroutine call? You had to store x29 and x30 onto the stack, right? Okay, so you had to do that so that when you hit the return at the end of that subroutine call, you knew where to go back to. Okay, and the architecture and the instruction set for ARM was such that you had to explicitly remember to store x29 and x30. Okay, now what were x29 and x30? X29 was the link register and X30 was the frame pointer. Okay. So you had to store those to the stack, okay, and wherever the stack was. But you had to do it. Okay. And then at the very end of the subroutine call, you had to pop those two things back off the stack and then return. Yes? Okay. Now, 6502 is nice in the sense that you don't have to explicitly store the program counter to the stack when you make a subroutine call. That's built into the instruction. Okay, so when you hit here at the very top, All right, so let me reset this actually. Okay, so what is our program counter at the very beginning of this program? Yes, and in this particular case, the way that Nick has designed it is that your program starts at memory address 600. Okay, there's nothing particularly special about that number. It just had to be something.
So does it start off with the reset factor?
He probably has it programmed that way in the background, but since this is an emulator, like it doesn't really matter, right? Okay, so we started address 600. Okay, now let's look at the disassembly here. Okay, what's the very first instruction there? JSR 0654. Okay, and there's the encoding of it. Okay, and what is it? 2054-06. Okay, so let's think about that. What does the 20 indicate? That's the opcode for jump to subroutine. Okay, what is the 5406? That's the address to jump to. Okay, so here the address to jump to is 0654, because remember it's all written in low byte, high byte order, right? Okay, great. Okay, so there's the 3 bytes. Okay, so the 205406 takes up 3 bytes. So that's memory addresses 600, 601, and 602. Okay, so if I step a single time and actually execute that instruction, 2 things are going to happen. Okay, if I read all 3 of those bytes in, okay, what is my program counter? Okay, so I have to read at a byte, a byte, a byte, right? My program counter starts at 600. Okay, it's going to go up, well, not necessarily by 3. Okay, it really just went up by, it looks like it went up by 3. Okay, and the reason that it's not always 3 is because, so you see here, not every instruction is the same length, right? And so on ARM or on Brookshire, right, when those of you guys who did 101, it went up by 2 bytes every time, because on Brookshire, every instruction was 2 bytes, period, end of statement. Okay, that's not the case here, where the instructions can be anywhere from 1 to 3 bytes. Okay, this is annoying in the sense that you don't necessarily know that you've finished loading in an instruction, but it's nice in the sense that you're not wasting memory. And I think last time we talked about how memory was the limiting factor on machines of this day, and so the architecture was designed with that in mind. Okay, okay, so we just jumped to a subroutine that's located in memory at 0654. And so now what's the program counter? 0654, because I just jumped there. Of course it should be that. Okay. Yeah, that's where I'm going to load the next instruction. Okay. But 2 things happened when I executed that instruction. Okay. Oops, sorry. Well, actually maybe 3 things happened. The program counter is now 0654. Okay, that makes sense. But what is the stack pointer? Now it's FD, and let's look at my stack. Okay, so down there on the bottom right of the screen is the top of my stack, which right now only has 2 bytes on it. Okay, and what do we see there? 0206. That was the value of the program counter immediately before I made the jump. Okay, and so when I hit the return from subroutine at the end of this init routine, okay, then what that'll do is pop 0206 back into the program counter, increment it by 1, and that's perfect, because where's the next instruction after I come back to it? 0603. Okay.
Why did it stick RTS right at the start test memory?
What do you mean?
Like if you go 3 down with the third subroutine,
Oh, the
then it
RTS.
just sticks RTS at the very beginning. And wouldn't you want that at the end?
So,
Then it's just gonna return out of it. Why?
okay, it never actually will execute that instruction though.
So what's the
Oh, I'm sorry, the test memory.
yeah?
Yeah. Oh, I see what you're doing. Saying, yeah. Basically, he probably just threw that in to basically kill it without having to delete everything, right? So Rippy's point is, why is this here? Well, now it's not there anymore.
Just
He probably just wrote it in as a
like bad
test,
code.
basically, right? Because what that would mean is that the test memory block of code was not actually getting used because it would jump to it and immediately return back
Oh,
from it.
okay. So that was probably just a debug tool.
Yeah. Okay. Yes, Cole.
Can we go through like every instruction? Like this.
Oops, not that. Well, okay, sort of. Yeah, sort of. Okay, so let me reset this and let me step it once. Okay, so notice, what is our stack pointer to start? FF. There's nothing on the stack. Okay, so when I hit this first instruction, okay, the program counter changed, the stack pointer decremented by 2 because I have put 2 bytes onto the stack, and this is how it handles the subroutine calls and knows where to come back from.
It's only so deep.
Well, okay, it can only go so deep. Okay, so when you push stuff onto the stack, right, how big is the stack at most? Well, the stack is the first page of memory, which is 256 bytes. If you're pushing at least 2 at a time, then sort of the hard upper bound on how many subroutine calls, how deep you can go, is 128. Okay. That are nested. Okay. So if we wrote, for example, our Fibonacci routine recursively, and now it's going to be worse than that, because in the Fibonacci's, what did we have to do when we did this in ARM? You had to store temporary values on the stack as you went. Okay, so in addition, you did.
You could just use extra register.
Uh, you could, but to do it properly, you really were using the stack. Okay, which meant every time you made a subroutine call, you were actually using like 4 bytes of memory, 2 for the return address, and 2 for the temporary values along the way, maybe more if they were 16-bit or something. Okay, but point being, you're going to be using up the stack pretty quickly. Okay, so our program won't be able to do the 50th Fibonacci number. The stack will overflow. Okay, that's okay. Yeah, why do you think it's called Stack Overflow? Yeah. Okay. So, uh, so JSR took us to init, which is down here. And what is this going to do? Well, what's this instruction? Load the X register with 0 and load the accumulator with walls. Okay, now what is walls? That has to be defined somewhere. Walls is, yeah, I could do that. Okay, DCB, it's D. Okay, so it has the value D. Uh, Rippy?
Gosh, Ricky, you just got demonetized.
Yeah, you're going to get me demonetized. Okay. And banned.
The botanical garden.
Yeah, well, okay. Rippy's going to be doing a whole lot of soldering. Yeah. So, jerk face. Okay. Um, I think it actually may be decimal coded as a binary, but I'm not sure because yeah, whatever. Okay. But point being, it's just going to load A here with the number D. Okay, that's it. Okay, and then what? Um, draw exactly 256 pixels of wall at top and bottom. Okay, so here we have store 200 comma x and also store 400 comma x. Okay, so the way that he designed this is um, the screen part. Okay, is that the screen memory starts at address 200. Okay, whatever. It has to be somewhere. In the same way that, like when you guys did the print without print in BASIC, you started at address 1024. Okay, whatever. It has to be someplace. Um, but what this X thing does is I'm going to store to 200 offset by X. Okay, so you guys remember with ARM when we put stuff in brackets and we had X0, X1 or something like that, we could store to a particular location offset by another value, right? So we had relative addressing. That's basically what this is, just looks slightly different. Okay, and so the X and the Y registers, you use them for indexing offsets. That's why they're called index registers. Okay, so if I did here store value f in this case to so what is x going to be at the beginning? 0, okay, because I haven't done anything yet and I've initialized it to 0. So I'm going to store the value f to address 200, okay, and then also to address 400, okay, and then I'm going to decrement the x value. No, it's actually going to go backwards, okay. So the x registers the x and the y registers can be decremented or incremented with a single instruction. Okay, so DEX, DEY, or INX, INY. Okay, that's nice, right? Because how often do you need to add one or subtract one while you're running code, right? Anytime you're doing a loop or something, it's going to be that. Okay, all right. So decrement X will take X and yeah. Now, so you notice that it put 2 pixels and then it started over on the right. Okay, if we're going to decrement X, what we should have done is actually loaded it as 256. Because, yes, okay, why is it not? Oh, what did I forget, gentlemen? Nope, nope. All right, because it's in hex, okay?
What did it load in otherwise? Nothing?
Well, it gave me an error because it's like FF. Well, it is an immediate value, but right. And so I didn't need to have the dollar sign with 0 because 0 and hex and 0 and decimal are the same thing. Okay. So now if I step, you see it starts from the right. Okay. So let me actually change that back to 0. Yes, but it did the left. You see how it's got those two green dots on the left and then it came over to the right? Well, it's because he started with 0. Okay, so what it's going to do is it's going to go to 200 offset by 0. Well, that's 200. Because if I decrement x, if I take 1 away from 0, what do I get? Or 255, right? Well, okay, so what's the binary encoding of -1? FF. Yeah. Okay, so it's sort of weird that you have to kind of think of numbers as both being signed and unsigned as you go, right? Offsets are always unsigned. You can only be offset by a positive number from a base address. You can't go negative. Okay. Um, that's just a limitation of the architecture. Okay. So that's why the way it was originally written put the thing here at the left and then came back around to the right, because it started at 0 and then it's 255, and that's going from the right, and then 254, 253, and so on, and it's going to keep scrolling to as we go. Okay, does that make sense? Yeah. Well, no. So this would be like doing poke 1024 plus X. Well, right, but if the X starts as the right side of the screen and you decrement that X value each time, or whatever it is, yeah. Right. Okay. So there we're thinking of it in terms of character spaces as opposed to pixels, but okay, whatever. Same idea, right? You're using a variable as an offset, and then you also have a base value of whatever it is. Okay. All right. Now, most of the instructions that involve arithmetic, okay, so you remember in ARM when we talked about the difference between mul, or let's just say add, how many different add commands were there? 4. And what were they? Add, add C, add S, and add CS. Okay, so what was the difference between all of them? You could take into account the flag, you could set the flag, you could take into account and set the flag, or you could just ignore flag. Okay, and when I say flag, which flag do I mean here? The carry flag. Okay, so you do not have that many instructions on this guy, right? So there is only one add instruction, or maybe 2 if you count the increment, okay, instructions. But basically there's just one, okay, add. But it's ADC, adding with carry. So a carry is, so the add with carry always takes into account what the carry flag is. And basically all of the arithmetic instructions are also flag setting. Okay, so if you do decrement X, okay, it is going to set the flags every time you run that. Okay, so what are the flags? Well, here they are. Yes, NV, negative overflow, B, D. I don't know what B and D are. Okay, or I, or sorry, I is for interrupt. Z and C. Okay, so the 4 flags that we really cared about for the most part when we were doing ARM was we had negative, overflow, 0, and carry. Okay, and the result of the operation when I decremented here. Okay, so when I decremented to get so 0 turned into 255. What popped? My negative flag popped because I just decremented a value. Okay. And also my carry flag is set here. Okay. So if I want to do an addition without a carry, what I have to do is clear the carry bit, then do the addition, and then reset it. Okay. Which is maybe a little bit annoying, but c'est la vie. Okay. Now, what's nice here is then the results of these operations are also going to set flags, and then we also have some comparison things, right? That makes sense. We had those in ARM also, okay? So we've got this instruction here, CPX0, okay? So what do we want to do? Well, we want to keep counting backwards until our X register hits 0. And once we do, then we want to do something, okay? Compare X, okay? And then what do we need to specify to do that? What we want to compare it to. Okay, so X is the X register. And what do I want to compare it to? The number 0, okay? To see if I've come all the way back around. Okay. And then based on that, I want to branch on not equal. Okay. So if X is equal to 0, the flags are going to get set in such a way that the branch on not equal will either trigger or not trigger. Okay. So branch on not equal, we had that with ARM. And so if the thing is not a 0, then what does it do? Draw initial walls, jumps back up, and does the same stuff again, but now X is 1 smaller. Then it will not do this jump, and it will continue to the next instruction, which is load A with the number 10 and store it to memory address 80, and then go on and do the remainder of the program. Yeah, it's just drawing the top and the bottom boundary. Okay. All right. But in terms of our, what's happening programmatically here, right, is, in fact, hold on one second, Cole. Okay, is this different than what it was before? So if I comment this piece of code out, looks the same, right? Okay, so is this instruction necessary? Well, yes, branch on not equal to 0. It didn't actually need to be there, okay? And the reason is that all of the arithmetic instructions are all flag setting, okay? So the decrement X is going to set the flags the same way that the comparison would. So the comparison is actually unnecessary here because we hit it immediately after doing something to the X register, okay, which is the very same register we're looking at, okay? So we would need the comparison if we were doing other stuff in between the decrement and the branch, but we're not in this case, and so I could comment that out with no effect whatsoever. It's not. It doesn't know that. Okay, branch on not equal. It's branch on not equal to 0. Yeah. Branch on not equal to 0. Yeah. Well, okay, because let's think about it. These branching instructions, how do they know whether or not to branch? It's all based on the flags, right? Well, which flags? Okay. Yeah, so the comparison is going to set flag, but my point is all the arithmetic instructions are already going to set the right flags. Okay, so if I hit that decrement X, the flags are going to get set to be whatever. Okay, and that's all I need to know for the branch on not equal. Okay, so branch on equal and not equal are essentially, you don't need to do a comparison if you want to branch on 0 or not 0. Okay, The difference would be if, let's say that I wanted to branch when it hit. So let me just do this. Okay, so what did I do? I had it stop early. Okay, so I would need to do a comparison if I wanted to branch, like when it hits a specific number and that number is not 0 that I'm checking for. So if I want to say count up to 17 and stop when I hit 17, then I would have to do a comparison. But the better way to do it is to count down from 17 to 0, because then you don't need this compare instruction.
Quick question: when it's moving stuff left and right, is it doing this in parallel, or is it
No,
just like, I don't know.
it's just fast enough that it doesn't. Like if I single stepped through it, you would be able to see individual rows changing.
Really?
Yeah,
It's like one thing happens at a time. It's just fast.
it's just really fast.
Okay.
Puts
Okay.
them on the right, and then as time goes on,
Yeah, it's doing some shifting and stuff, but
Does this have parallel course, or you know how just one?
dude, consumer computers didn't have multiple cores until the mid 2000s, right? Like the first computer I got that had multiple cores was I got an iMac that had 2 cores.
Dual core.
I got a Core 2 Duo.
So why didn't someone, I don't know, buy 2 Commodores, rip both the cores out, and then reassemble it somehow with 2 of them?
Because that's a lot more complicated than you'd think. Okay, now symmetric multiprocessing, multiple core machines, it was actually multiple chips, right? Each chip was independent, and you had to have a motherboard that could support that. Now, there was parallel stuff back in the day, but it was like Cray stuff, and it cost thousands upon thousands of dollars, right? But your average Joe home computer was single processor, and that was like that until, like I said, the mid 2000s, right? I mean, if you think about it, right? Like, okay, how many cores are in my laptop? 8, right? So it's not that inconceivable that not that long ago there would have been only 1 or maybe 2. So yeah. Okay, so let me stop that. Okay, so what I'm going to have you guys do, okay, is, and we're of course woefully short on time, which, okay, there's one reason that we're woefully short on time, and what is it, guys?
some people are showing up.
Some people are late and not ready to begin with their buckets and all of their stuff at 9:45. Do you think we could fix that, please, next time? Okay, thank you. To be early is to be on time. Okay, and also you can move your bowels on your own schedule, not during class. Okay.
I'm sorry.
Okay.
It's like a schedule.
All right, Sheldon. Okay.
It's like a schedule. I can't help that.
That's fine. You're human. I'm not. Okay. Okay. So next week, what I want to talk about on Tuesday is hardware interrupts. Okay, because that will be relevant to the sort of breadboardy thing. I need to post a bunch of stuff to Canvas, um, and I'm going to have you guys are going to write a piece of code that'll go in here so that you can simulate it and check to make sure it's reading and doing things correctly. Okay. Now, the other thing that's going to happen next week, I believe on Thursday, I'm pretty sure I've got that right. No, I don't know about that. So, did anybody go to the art exhibition that opened in February?
Yes, it was so cool.
It was really cool, right?
It was so cool.
So, Rippy, why don't you tell them about what the cool art was?
So like it was all about like electronics and art, and like I thought one of the coolest things was like a dirty mixer, where basically it was like a piece of fabric that also had a bunch of, it was conductive fabric, and then depending on where you took the clips, and put them on the fabric, it would change how the screen looked because of the different connections that existed on there, so you get more or less resistance between it. So you can make it look so different, you just put it in different random places on the fabric. And that was just one of the really cool things. They have like.
So next week, that artist is coming back to Wabash, and next Thursday she's coming to our class.
Wonderful. Good to see her again.
Yeah. And to talk about what we're doing with the breadboards and that sort of thing. And that's cool, right? Huh? Okay, so yeah, so that's what we're going to do Thursday. No. Is talk about sort of digital art and like, you know, the cool stuff we're doing, right? Yeah, she was. And that's why do you think I asked her to come to class? Okay, so, right. Okay, so pay attention to Canvas, start showing up on time, damn it. And anything else?
I met with the dean. He said there's some senior chapel next Thursday, or there's something.
11:10.
Oh, like something for graduation.
It's not on
It's
Thursday.
like making sure you don't have like.
It's on Tuesday.
$10 whoever gets his email.
Okay, it's on Tuesday, so we don't have to worry about
Oh,
it.
it's on Tuesday.
Okay. All right, I will see you guys later.